So what we saw in the last video was this idea of a energy level diagram, and we talked briefly about absorption and emission spectrums. Remember, for an absorption spectrum, what you have to have is you have to have some photon passing through what we like to call a cold gas. And what happens is most of the light gets through it, but certain wavelengths of that light are absorbed. And we see that absorption as dark lines in the absorption spectrum. On the flip side of things, if you have a hot gas, then this gas is excited. That's why we call it hot. It's really just an excited gas. And this gas, as the electrons are from a high energy level and drop to a low energy level, they can just give off photons. This is what we see for things like stars. Okay? So a really cool thing with that for absorption and emission spectra. Now, one of the things that was noticed early in the era of modern physics are these emission spectrums. We had spectrographs, diffraction gratings from the optics unit, and we were noticing emission spectrums just like this. Well, it turns out that this specific emission spectrum is the emission spectrum of hydrogen. Elemental hydrogen is that right there. Now, there are some other things that stars have in terms of helium and composites and whatnot, but we quickly figured out, and it was shown that by J.J. Balmer, that the following equation, 1 over lambda equals R times 1 over NF squared minus 1 over NI squared. Where lambda is the wavelength that each of these, lines of light are at, and each one has its own wavelength here. Wavelength. Ni and Nf are the initial and final positions of an electron transition. So, if we think back to our transition levels we had the other day, because this is giving off light, this could be the initial and this could be the final. And we'd be going down in transition. And it would give off a photon of light, which would have some wavelength. Okay? This R here is what is referred to as the Rydberg Constant. The Rydberg Constant is 1.1 times 10 to the 7th inverse meters. So it's like 1 over meters. Now, something really interesting about this equation is that this equation was set up to plot and fit spectral hydrogen. And it fits spectral hydrogen perfectly.
Just harpoon him out.
Now, while this works for spectral hydrogen, it doesn't work for helium. It's like a little bit off. It's really close, but it's a little bit off. And we get into heavier elements, like lithiums and carbons and oxygens. Like, this isn't even close. So, something is going on here. But for hydrogen, this works perfectly, okay? In general, what Balmer was able to show here is that for hydrogen and for what we see for this visible emission spectrum, these emission lines here could be determined by setting NF equal to 2. If your Ni is 3, we'd get some line. Ni is 4 would give us a different line. Ni of 5 gives us a different line. This is what Balmer gave us. And this is in the visible spectrum. However, I would like to have fancy lines named after me too. So, what do? I change NF to 1. Because now, I don't go from 3 to 2, I go from 3 to 1, the ground state. Ho-ho! Different energy drop, different photon of light. These were found by Lyman. And these are in the ultraviolet. This is why Balmer didn't see them initially. You could physically see the Balmer emission lines because they're in the visible spectra. Ultraviolet, we can't see in ultraviolet as humans. So we need some sort of detector to pick that up. Maybe you want to have your name tied to a number of lines. So what do? You pick a new number. We pick 3. These are passion lines. In this case, we're starting up higher, which means that these lines are tighter together. And we're coming from things like 4 or 5 and winding up at 3. Boop. As a result, there's a smaller drop. A smaller drop means less energy, which means these lines are in the infrared. So Balmer, Lyman, Paschen lines, they're all lines that follow this equation and can be found for spectral hydrogen. Now maybe you're like, I want my name too, pick me, pick me, pick me, and you pick NF equals 4. Okay, we get the idea already, you don't get a fancy name. These are the only people who get fancy names. But you could do this for NF equals 4, for NF equals 5, for NF equals 6. There's nothing wrong with that. But these were the first ones before we really had like a large idea of what was happening. So they get fancy names. Or rather, they get their names named after them. Okay? We're not going to touch this equation very often here, but it is a nice equation to have, especially if you're ever doing spectroscopy. Depending on what band passes you might be looking at when you're looking at stars, possibly in your future, then you might accidentally get some of the Balmer, Lyman, or Paschen lines to be in your spectral region, which will effectively mess up your data. So they're important things to understand, recognize, and see what's going on there. This idea and this Rydberg constant will come back a little bit later, but for now, this topic is finished. Till next time, adios, and take it easy.